Welcome everyone and welcome back to lecture. We're going to cover section 11.1 this time. 11.1 is going to be concerned with seeing if there is any relationship among data members. So let's say that if we had some fertilizer and we're going to put fertilizer on some garden plant, regular plant, we put a little bit in there, we note the growth over a period of time, let's say a day, we add, if it takes twice that, 2 ounces per square foot, note the growth. And then we're going to see, is there any relationship between fertilizer and the growth of plants? We kind of feel that there is. They put a lot of fertilizer out. But is there any way that we could absolutely tell? And that's what we're going to talk about this time. 11.1 is concerned just to see if there's any relationship between those two variables, the amount of fertilizer and the amount of growth in a plant. That's called correlation. So we're going to first talk about correlation, and then we're going to see that we can do, if there's some correlation there, then maybe we can do some predictive calculations. So given that there's some correlation, we'll do some regression analysis to determine an equation. If I put this much fertilizer on, what kind of growth would I expect in the plants? So let's get started. I'm going to do away with me and we're going to get down to lecture. So correlation, section 11.1, we'll talk about scatter plots, computing correlation coefficients, compute them, interpret them, and understand that correlation is not the same as causation. Okay, so in some cases we'll see that there's some correlation, but one doesn't cause the other. Hopefully the fertilizer causes the extra growth. Sometimes we're not going to have that, and maybe we'll look at an example. So the first thing that we would want to do is construct a scatter plot. So suppose that a real estate agent wants to study the relationship between the size of a house and its selling price. It's reasonable, we know, to suspect that selling price is related to the size of the house. Larger houses cost more. Specifically, we expect that houses with larger size are more likely to have higher selling prices. They're more costly to build, more things are in there, more wood, more resources. So a good way to visualize a relationship like this is with a scatter plot. In a scatter plot, each individual in the data set contributes an ordered pair of numbers, and each ordered pair is plotted on a set of axes. So they've done this for you. They said, here's the size of the square foot, and here's the selling price in thousands. So this is a $400,000 house, $426,000 house. And if we put this in a scatter plot, this is what we would come by, okay? It seems like that the more square foot, the higher amount of square foot, it looks like the price kind of goes up. 3,200 are up around this area. Here's some at 3,000, and then the smaller. And that sounds reasonable, okay? So on the TI-84 Plus, you can do that directly. We've seen this in a couple of cases in labs where you can do the L1 and L2. Well, what you would do here is put, here would be the L1 values, which is the square footage, and here's the corresponding selling price that that house was sold for. And then here's the instructions. Basically, you let it know that you're in L1, L2, X list, Y list. The X is the independent variable. This is basically saying I want to know from the square foot, is there a relationship between the price? My Y list is my L2, and then you're just telling it that you wanted to do a scatter plot, and then you do this zoom 9 to view it. So for one thing that we have available now is online. We can certainly use Excel to do this. Here is a 2 list of numbers. I have some X values and some Y values, and basically I want to do a scatter plot and see if there's any relationship in here. So if I go here, we've kind of done scatter plots before in the past, doing different things. I would do insert, and then I would go up here, scatter plot, and pick out one, and that would be our scatter plot. I would go here, do a title. I can add different, do the axis titles, axis, so I could do left and right. Axis titles and change those, do some data labels and different things, okay? I'm going to use this trend line later on, so remind me to do that. Okay, so this is the scatter plot, and here we see this thing is absolutely looks like there's some relationship between here. The bigger I get along the x values, these numbers, the higher I get along here. So there's some relations. One changes, the other changes, and this is a nice linear means a straight line relationship. So let's go back to lecture. Our lecture slides from the current slide, and let's continue on. So this idea, there's a couple of ways that we describe this. This is, if I can kind of see, now this isn't that straight line like I had in my Excel chart. This kind of goes up and it's around, but notice that if I can think about this, it appears that there's like some straight line that's kind of in the middle of all of this, and there's not some big curve that's going on, curve down, up to down, other things. There seems to be just some general points along this, and they're all along that straight cluster. I would say a cluster of these things, okay? So what we would do is say there's some linear association. If when we go increasing, this is from smaller to larger, smaller or larger along the y value. If we increase here, that they increase here, we decrease, they decrease. This is called a positive association. And if this one, as this increases, that increases, they both go increase to the right. That's a positive linear association. So it's increasing, it's a positive association. When one goes up, the other goes up. That straight line says it's a linear relationship, positive linear association between the two. So two variables are positively associated. Large values of one variable associated with large values of the other. So if I get larger along the x, the larger along the y. Now I have to kind of envision a straight line being through here. Okay, I have to picture in my mind that there is, if I can pick out my point, that there's something that goes through here. That should be a straight line. That's just my drawing. Here, notice that as I go, this thing gets smaller. As I go to the right, the y value goes down. Here, as I went to the right, the values went up. So this is a positive association, positive linear because there's that straight line in there. Negatively associated, as I increase one, the other one goes down. And linear because it seems to be all in a straight. It doesn't go up like this. So it doesn't go here, and then all of a sudden, by the time we're up here, it's just getting larger and larger. Or decreasing and then decaying out. Two variables have a linear relationship, but the data tend to cluster around a straight line. Cluster around a straight line when plotted on a scatter plot. Now, when we did it on Excel, just that very one, it was just, you know, directly on that straight line. It's not always going to be that. Okay. So is there some way, that's an observation way, but is there, it's hard to visualize and see how tight those dots are clustered around that imaginary straight line. What we would like to do is come up with a number that would work for us, that we could compare, that we could share. And this is what this is. It's basically called the correlation coefficient. Here is the long calculation variable. Given some sets of values, x's and y's, sample means x bar and y bar. Here's the standard deviations of the x's, the standard deviation of the y's. These are all samples. We don't assume that we've got all of the population. If we did, we'd kind of be doing something different. Okay. So here's our R. We're going to do 1 over n minus 1 points. We've got n points, okay. Sample size is n, 1 over n minus 1. And this says go for each one of these, x sub I, y sub I. multiply each one of these out like x1, y1, x1 minus x bar. So you would do x1 minus x bar over s of x, y1 minus y bar over s of y plus x2, the second one, minus x bar, y2, the corresponding y2 minus y bar, s of x, s of y. And then I would do the next one all the way up. This would do all n, and I would just add these two together. Once I've added them, I would multiply times 1 over n minus 1. And that would be my correlation coefficient. Okay? So here is kind of the summary. Once we do this calculation, here is your check. You should be between -1 and +1. If you get r less than -1 or r bigger than 1, you're wrong. Just start back over, reinterpret, go do some practice problems with answers, get that process down, come back and retry again. Okay. -1 less than or equal to r less than or equal to 1. Negative correlation, negative. And this, the positive sides between 0 to here, these are positives. Positive with the r value of 1 is that straight line that we saw in my Excel plot. This would be decreasing along a straight line. 0 would be there was basically no correlation in there. Doesn't matter which one you treat as x and y. If you have a relationship between x to y, there's a relationship between y and x. Okay, only measures the strength of the linear relationship and when it's positive or negative. Okay. This thing is sensitive to outliers and can be misleading when outliers are present. So here's an example. Basically, we went back through, here's our example that we worked before. Here's our x bar, our y bar, s sub x. So basically we went through here, did equal average in Excel, maybe. Along for our y equal average of these, there's our average. Standdev.s to give us our standard deviation in the x's and the y's. And then here is for each one of these things, I go x minus x bar, y minus my y bar. And I calculate all of these, multiply them together, and then I basically add all of these things together. That's the sum, and then divide that by 7. So that correlation coefficient R is 0.90, a strong positive correlation. You can do on a TI-84, this will give it to you, linear registration. The 36 also has these available so that you can put them in your calculator. Okay, and then we just basically put it up. Here's a mini tab output. Pearson correlation is what we're calculating here. That's the correlation 0.901. The p-value says, yep, this is pretty obvious that we've got some relationship there. Okay. Here is how we did it in Excel. Now what I'm going to do is kind of bounce back to my, so I want to keep those. I want to go back to my Excel. The correlation, I want to calculate this correlation, equals, I'm just going to type in Correl. I see it pop up. There it goes. It says give me the array 1 and array 2. Array 1 is just my x values, just the values. I go back up here, comma. Give me the y values. Close up my parentheses, And then this is my correlation coefficient for this. Correlation is +1. There's basically a strong, remember we saw, if we go back down here, that's everything lied along that line. If I use this line as a predictor, basically this graph, everything's along this line. That's what that's telling us. Positive, one increases, the other increases. This one goes back down, the value of the y's go back down. So that's the correlation coefficient. Let me do this over 1. I missed. That looked kind of strange. Let me fix that. Okay. So let's interpret the meaning of the correlation coefficient. Again, the correlation coefficient can be interpreted as follows. If R is positive, the two variables have a positive linear association. If R is negative, the two variables have a negative linear association. Naturally, we have to worry about how strong that association is. And if R is 0, the linear association is that there's basically none there. Okay? Weak linear association, well, that's assuming that there's any linear association, but it's a weak association. The closer R is to 1, the more strongly positive the linear association is. The closer R is to -1, the more strongly negative the linear association. When it says strongly, the more it lies along that straight line. Okay? If R is equal to 1, then the points lie exactly on a straight line with a positive slope. If R is equal to -1, then the points lie exactly on a straight line. Negative slope, positive slope means going up. One increases, the other increases. This is one increases, the other decreases. Okay. These are called perfect positive linear association and perfect negative linear association. So when we had mentioned at the very first, is correlation causation? Basically, when I did that, did I move that X and actually cause the Y to change? That, maybe, maybe not. Here is one where, when we did the fertilizer, we can assume that there was some correlation there, okay? We needed to tweak the values that I used, ounces, maybe some more, but hopefully there's something there that fertilizer, if we fertilize, that's going to increase plant growth. But not everything, just because there's some strong correlation, does it mean that one caused the other? So this is kind of an example of this. We took a group of elementary school children, took a vocabulary test. It turned out that children with the larger shoe sizes tended to get higher scores on the test. And those with smaller shoe sizes tended to get lower scores. As a result, there was a large positive correlation between vocabulary and shoe size. Now here's the question. Does this mean that learning new words causes one's feet to grow, or that growing larger feet, causes one's vocabulary to increase? The fact that shoe size and vocabulary are correlated does not mean that changing one variable will cause the other to change. If I could stretch out somebody's shoe or foot size, that does not mean they're going to have a larger vocabulary. So why, what other thing is going on here? Basically, when a person grows, they have larger feet. So they may be, comparing 6th graders, 5th graders, 6th graders, 7th graders to 1st graders, 2nd graders, 3rd graders. Naturally, those with larger feet, the older children are going to have a larger vocabulary. So this correlation, even though it was correlated between the feet size and their vocabulary size, it wasn't a causation that I couldn't just stretch somebody's foot and get an increase in vocabulary. That's the causation part, okay? So what we were trying to say here is that correlation is not the same as causation. In general, when two variables are correlated, we cannot conclude that changing the variable of one variable will cause a change in the value of the other. Okay. So we'll see you in the 11.2 lecture. We'll continue on with that Excel spreadsheet and do some other things to it. Thanks.